welcome to this video on fluid fundamentals. This video will be about the hydrostatic equation, and we'll be discussing what it looks like and how it's used. So the hydrostatic equation applies to a static system. It has three terms: pressure, P, rho gh, also known as hydrostatic pressure, and P naught, referred to as total pressure. So the rho is the symbol for fluid density, g is the gravitational acceleration, and h is the depth of the fluid. So the hydrostatic equation is really important. It's going to be looking at fluids that are not in motion, but the logic and the mathematics does apply to fluids in motion as well, which makes this a fundamental aspect of fluids. So many aspects of practical fluids can be understood through the equation. It's essential to understand the equation to solve tough fluid problems, but you can solve simple problems too, like in order to design dams, silos, and other applications in water engineering. So dams are a really common case that are used to appreciate the change in static pressure. So the figure on the left is a dam, and we're going to take a height h from the surface of the water going downwards. So note that h will be negative. So when you actually solve this equation, P is going to increase as the magnitude of h increases, or as h decreases, as h becomes more negative. So the equation shows that pressure increases linearly from the top to the bottom of the fluid. The pressure at the top of the dam, in this case, is P naught, and the pressure at the bottom is P naught minus rho gh, which is a higher pressure again because the h is negative. You'll hear very often signage, and taking a lot of care with signage and understanding what's happening is going to help you avoid making mistakes. The equation also applies to pressurized vessels, for example, liquid hydrogen in a rocket. So a tank may be pressurized at 10 megapascals, but pressure is still going to be higher at the bottom of the tank versus the top of the tank, even if the tank in general has been pressurized. So you're looking at, in the case of hydrogen in a rocket tank, you just need to establish what the density is, what the height of the tank is, and what the total pressure is. So what we can establish is that if we lay out the hydrostatic equation at the top, P plus rho gh equals P naught, we establish that the tank is pressurized, so P naught equals 10 times 10 to the 6 pascals, i.e. 10 megapascals. So what we're really looking for is the size of the rho gh term. So I can tell you that the density of liquid hydrogen is 70 kilograms per meter cube, that the gravitational constant is 9.81, and that the height of the tank is 25 meters. And this means that the pressure at the bottom of the tank is going to be 17.4 times 10 to the 3 pascals higher than at the top of the tank. But we also want to establish what this actually means for the design. So this is the question I pose at the end. What observation can be made about this? The observation that can be made about this is that 17.4 times 10 to the 3 is nearly 1,000 times smaller than the pressurization of the tank itself. And what this means from a practical perspective is that there is virtually no difference in pressure between the top and the bottom. That the pressure at the top of the tank is 10 megapascals, the pressure at the bottom of the tank is 10 megapascals and a little bit. And this is important from an engineering perspective, is that often we're only interested in the numbers that are going to actually make a difference to the design. And in this case, we went through with the maths and we established that the consequence of the maths is unimportant, and that happens sometimes. And sometimes the maths is really important, sometimes the maths is inconsequential, and sometimes it's somewhere in the middle and we need to make a judgment. But anyway, that's everything for this video. Thank you for listening. I will be releasing more videos on the hydrostatic equation, such as derivations, just to nail in what exactly the hydrostatic equation is and why it works. Thank you for listening, and we'll see you later.